So we've got a financial advisor. He has got 3 different accounts that he can put a client into. The client wants to retire, and to retire they want to double their money. So which account should we go into? Again, we have account X, Y, and Z. Account Z is the one that's right over here, and it says right here the graph is in the balance of account Z. So on the x-axis we have years, y-axis is balance. So in year 0 we have $1,000, and when do we double our money? We double our money at 6.9 years. So it's going to take 6.9 years for this account Z to double. Looking at account Y pays 6% compounded quarterly. 6% compounded quarterly. So we're going to use our any compound formula, which is P times 1 plus R over N to the NT, which means this is 1,000 times 1 plus 0.05 divided by 4 to the 14. And what we're going to do is drop in a 2,000 line here. Again, we know we're starting off with $1,000 on account Y. And when we graph this function, 1,000 times 1 plus 0.05 divided by 4, remember we're compounding quarterly, so we're going to divide by 4, and that means we'll also multiply by 4 up here in the exponent. When we graph that function, it comes out like that. So here's Z, here's Y, and this coordinate point right here was 11.6 comma 2,000. So 11.6 years. And then X says X is 5% compounded continuously, and our continuous formula PE to the RT. So 1,000 times E to the point 0.05. Sorry about that. This was a 6% annual interest rate, so we should put 0.06 here. Okay, so now when we go to graph this new function for account X, again, we're starting here at the same $1,000, and where do we get to this $2,000 line? Well, when we graph it, we intersect with this 2,000 line at 13.9. So here's going to be our account X curve. And that's it. We've got all 3 accounts listed out and how long it's going to take for them to double their money. This means that the advisor should choose account Z because it doubles the money from $1,000 to $2,000 the fastest. And you can see that right here. This is your time. So whichever one of these curves is going to cross the $2,000 line first, and that's this one. Okay. So now they give us 2 quick problems. A lab has 140 cells present. During the first 8 hours, the number of cells increases by 13% each hour. Write an exponential model. So we're looking for an equation that is going to go from 140 cells all the way up to however many cells are dividing at 13% each hour. So this is increasing. It's a growth formula. If I'm going to take something like 0.87 and I raise that to when this is going to be about 200, I can tell that this is already not going to be what I'm looking for, because 0.87 is between 0 and 1, which means when I raise it to a power, it's going to look like this. This one here, I think it would be fine, but notice that this t exponent is actually going to get multiplied against all of the little exponents in here, which is not the same thing. This says we're taking the starting value and raising it to the time, and that's not our formula. So we know that this one's wrong as well, because they put the 140, the original amount, they put it inside of the grouping. And we know that it's supposed to be outside of the grouping like this. So on this one, again, we've got a number between 0 and 1 here. When we raise it to a power, it's actually going to look more like this. So this would show that our cells are declining. And here's our last one, 1.13. Again, this is greater than 1, so when we raise it to a power, it's going to grow for us like that. This is the only one that actually truly looks legitimate for this scenario. Rick invests 850 euros into a CD that gains 2.5 interest. Well, we may not know what the currency is, or we may not know what the specific, financial product is, but we do know our formulas. And if they're going to ask for something that is compounded monthly, then we're going to need this kind of formula right here, where you start with the original balance, and then you have the interest rate divided by, if it's quarterly, you divide by 4. If it's monthly, you divide by 12. If it's semi-annually, you divide by 2. So we're looking, if it's compounded monthly, for something that's divided by 12. The only thing that gives us this division by 12 is going to be right here. It's also raised to the 36th power, which is exactly right. So we know that this is also not true, because these are not the same thing. What's inside the grouping? 1.025 and 1 plus 0.025 divided by 12. These are not the same thing. So we don't want to make them equal. It's not this one. It's definitely not this one. And it's definitely not this one. G is the only one that actually gives us compounded monthly divided by 12. Okay. So for the pre-exit ticket, we've got a couple of exponent rules to look out for. E to the negative 2 times e to the negative 9 is e to the negative 11, which means 1 over e to the 11th power. So we have to take a negative exponent and make it positive, and that's going to give us c. Remember what we were explaining earlier, we've got 4 to the first power, and then e to the negative 3x power. So this 5 is going to multiply against the 1, and it'll multiply against the negative 3x. So 4 to the power of 5, e to the negative 15x power. Again, we don't have a very happy exponent here. We're going to make them happier and positive if we push it to the denominator. And 4 to the 5th is just 1024. So 1024 divided by e to the 15x. Again, on number 3, one of the easiest things to do is always just to make a t-chart. You can see here the coordinate point 0, 1 when x is 0, y is 1. So I'm going to take that common coordinate point, and I'm going to look down here, and I'm going to put in a 0 for x, hoping that I'll get a 1 at the end. So here's my zeros going in for my x. And 0.5 times 0 is 0. So this says y equals 5 times e to the 0 power. Anything to the 0 power is just 1. So this is 5 times 1. 5 times 1 is 5, not 1. So it's not this. And this will be the same thing, right? 5 times 1. So we don't want that one either. So look at this one. E to the 0 power, that is 1. And then here's e to the 0 power again. This is also 1. So we're looking for something that will give us a decreasing curve. And that is decreasing. And an easy way to think about this is, again, this is a negative exponent. And negative exponents can't stay where they are. They're going to go somewhere else. So this is actually 1 over e to the 0.5x. And now you can see whenever you increase x to 20, 100, 1 million, this denominator is going to get large, 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 and the numerator is going to stay the exact same. So yeah, we're going to continue this decreasing curve. There's our answer A. We skipped a few questions in the copies, but this is just our parent function. So when x is 0, y is undefined, and when x is 1, y is 0. So if we were to draw a quick graph of this, we could go over to when x is 1, y is 0, and then of course we know we have our asymptote here. When x is 0, y is undefined. Now we've got our parent function. Our domain will be x is greater than 0, and our range will be all real numbers. So let's come on over here. We can see that all that's happened, we did a base change, but the only translation here was that we went to the right 4 units. So again, all of these values, the x's got pushed over 4 units to the right. So this will be x and y. X is 4, and y is undefined. X is 5, and y is 0. So we'll come out here to 5, comma 0. We have an asymptote here at 4. There's our log function, and now our domain was when x is greater than 4, and our range will be all real numbers. We need to rewrite this in exponential form. This says 0 is the exponent of 2 to get 1. 0 is the exponent of 2 to get 1. So now we can write this out in equation format. 0 is the exponent of 2. Means that 0 is the exponent of 2 to get 1, like that. And anything to the 0 power is just 1, so this works out. So again, when we are trying to compound continuously, we just use PE to the RT. And we're going to start with $3,200. So 3,200 times E. And then to the R, interest rate is 0.08, and then we're compounding it continuously. So we're just going to do it like that. So we've got now an amount A after t years. In B, we want to find the inverse of the function and then describe what that inverse represents. So we're going to, basically we need to solve for t here. And that will be the inverse. Right now, if they gave me how much time they wanted to invest for, I could tell them how many years it would take. Or how much the final amount would be, excuse me. So the client tells me how long they want to invest, and I tell them how much is in their account. Now, if we flip this around, though, if we switch our t variable with our a variable, then we can ask them how much would you like to have at the end, and then I could tell them how long that would take. So you can see that the situation will be reversed. So that's what we're going to do. We're going to solve out for t, and to do that, I'm going to divide both sides by 3,200. So I have e to the 0.08t equals a over 3,200. Now I need to get this exponent away, so I'm going to take the natural log of both sides. When I do that, this will fall off, and I'm left with 0.08t is log in base e of a over 3,200. And then I just need to divide here by 0.08. Now that we're all done, we can just put this final expression for t into our calculator. And again, this is going to give us the inverse. Describe what it represents. Well, they're going to tell me a final amount, and then I get to tell them how long it's going to take. The exact opposite of this. So client tells me how much they want to make, or how much money they need. And I tell them how long it would take. Alright. So then they asked me to solve out if we want to double our investment in 5 years, would we reach it? So our initial investment was $3,200. Doubling that is going to give us $6,400. And when we solve this out on our calculator, we end up with 8.664 years. So we will not reach our goal. No goal met. We need 3.664 more years. Like that. No goal met just yet. We need 3.664 more years. All right.